morning, everyone. And I'm happy to be the last one before the lunchtime. And today I'm from the same institute as Professor Tang, who just gave you a presentation. And my topic today I'm going to talk about is experimental exploration of sodium chloride solution on the thermal behavior of phase change material. So the first of all, I want to introduce some basic information about phase change material. And I will talk to you about what the phase change material are and how they work and what function they have and how we can use it. Basically, the phase material, all the material, we have three phases: solid, liquid, and gas. And basically, if you want to transfer from one state to another state, you need energy or you release the energy. Normally, we're using the sensitive heat. So when we're heating the water from 0 to 80 degrees, you need to put 335 joule per gram energy. So you can get the 80 degree hot water. But if you're using latent heat, so if you're melting the ice to water from 0 to 0 and release 333 joule, so the energy almost equal heating the water from 0 to 80 degrees Celsius. So based on that, we can see that the latent heat has a huge energy storage properties. So we can utilize the latent heat for either storing the heat or storing the cold energy. Doesn't work. So like I said, so from PCM absorbed energy from environment through changing state from solid to liquid during the endothermic process, and they release the energy to the environment where changing the state from liquid to solid during the exothermic process. So basically that's what the PCMs are and how they work for storing the energy. And because I know we know the energy is one of the top problems for the human beings for the last 50 years. I think it still or will be the major issues for human being in the future. So basically, PCM during the energy storage area, it have many applications. For instance, it can be used for the solar energy system. We know the solar energy system is not very consistent system. Sometimes you have the sunlight, sometimes you don't have sunlight. And if you have plenty of sunlight, you can just use solar energy. But if you during the sunlight days, you can store the actual energy, either in the electricity or in the heat. And when you have short of the sunlight, you can just release it to use it. So basically, the PCMs can be used in this area. And the other one is in the building. So in the building, like smart building areas, you can use the PCM to store the thermal or the cooling. So I know in Stuttgart, Germany, they have some like this prototype buildings. So they just using like a PCMs without the conditioner to adjust the temperature of the room. So all over the year, you have always the constant temperature of 23 to 25 degrees Celsius, which is very comfortable for people. And also, it can be used in the fabric. So we can compost the PCM in the fabric, and then we have we woven them into the cloth or whatever other people, for people use. And the other area it can be used is for the IC, for electronic devices. For instance, it can be the cooling system in the IC area. And for the power system, also it can be used to adjust the peak and off-peak time electrical supplies. But the PCM is very good and very promising material for energy storage, but it still have some unsolved problem. The first one is a high supercooling degree, so which majorly just denied the applications of this smart material. And the low crystal growth rate also is another problem. Basically, the first problem is partially it's come from the second one, because it has a low crystal growth rate, so you have the supercooling or superheating problem. And also the poor thermal conductivity, because for the PCM, majorly, one of the major PCM, they are the polymers. We know the polymer has very poor thermal conductivities. So these are the three major problems we have for the PCMs for the moment. And in our previous research, we found if we add some sodium chloride into the PCMs, the pure PCM we used is they are the polymer. We can just improve the supercooling problem. Also, we can enhance the thermal performance. This is basically based on the hydrogen bonding networks of the ions with the water molecules. So as I said, in our previous research, we added a certain amount of sodium chloride. It can improve the formation of the emulsion and increase the yield. But after you adding certain level, it doesn't give you any improvement. This the experimental we conducted at the beginning of the research. It promote crystallization by heterogeneous nuclearization and also reduce the degree of the supercooling. That's basically the first we found, and then we did some deeper research on this topic. Then our research focused into the thermal performance of additive agent with various addition rates, and what's on the thermal performance with different concentration of sodium chloride solution. Basically, we have prepared various concentration of sodium chloride solutions. These are 1%, 5%, 20% in weight. And also we have set up a parallel experiment. So for each concentration solution, we have different adding rate in weight. These are 1%, 5%, 10%. And first, we can look at the effect of the adding different rate of sodium chloride on the thermal behavior of PCMs. And we found from the DSC curve, we found that axonal peaks shift to the high temperature side, and also thermal peaks shift to the low temperature side, which indicate that it can improve the overcooling problem. And also we found addition of 1% of sodium chloride. It can increase the latency from 180 joule per gram to 195 joule per gram. And then we carry on our research. We want to look for the effect of the adding different rate of 1% sodium chloride solution on the thermal behaviors of PCMs. And based on our research results, we can see all the peak temperatures, onset temperature and onset temperature, show a sharp alteration of 3 to 5 degrees Celsius. The degree of supercooling has reduced by 6 degrees, which is quite good. And after adding the solution, the latent heat of PCMs raised and become higher than those of octadecane, which is the pure PCM material. And also for the 20% of sodium chloride solution, we also carry on the same research. We want to look at the effect of adding different rate of this solution. What's the result? And also the results shows us that all peak temperature and onset temperature and onset temperature show a sharp alteration of 3 to 7 degrees Celsius, and the d-value of the peak temperature decreased and reached about 5.6 degrees Celsius. And we found by adding a small amount of substance into the PCMs, the latent heat tends to increase. And the next step, we want to we fix the addition rate, and we can see the different the sodium chloride solutions with different various concentrations. It's their influence to the thermal performance. So firstly, we fixed the adding rate at 1%, and we found that the latent heat of composite PCMs increases up to 113%, and the latent heat tend to increase, and the sodium chloride solution have more better performance in the the pure sodium chloride. Basically, when the concentrations goes up and the supercooling degree reduced. And we fixed the adding rate at 5%, and we found that all the peaks are found to be sharper and narrower than their counterpart displayed in the octadecane, the pure PCMs. And we found the sodium chloride solution is more beneficial for the thermal performance. And also we fixed the added rate at 10%, and we found although the supercooling of 20% solution is lower than that of a 1% solution, the latent heat is also decreased. And I think we also did some preliminary research about the reasons why we have these outcomes by adding the sodium chloride and its solution. And based on the classical nucleation theory, we know the sodium chloride, they are the small particles. When you add a particle in the polymers, it can be converted from the homogeneous nucleation to the heterogeneous nucleation. So that's probably the reason one. The second one, based on the dynamic Monte Carlo theory, the steam pressures and the critical physical separation side differ in different solutions. Basically, if you added the sodium chloride solution, it separates first from the composite, and then it can be changed the crystallization and the melting point. So that results in the improvement of the supercooling problem. And the third one is when you add the sodium chloride inside, it's not just like the small particles inside. It also reduces the content of the PCMs, the pure PCMs. That also improve the supercooling problem. And I have a quick draw of the conclusions. We found both the sodium chloride and its solution could enhance thermal performance of composite PCMs. And as the weight rate of additive increasing, the latent heat first increase and then decrease. At 1% of added rate, the latent heat of PCM's composite reaches the highest value. And sodium chloride solution is more beneficial than the sodium chloride, pure sodium chloride, in thermal performance and the same addition rate. And the PCM with the higher concentration of a sodium chloride solution have a better thermal performance and the same addition rate. And I want to use the last few minutes to introduce another area we have done in our research group, because we have carried out research on PCM for about 15 years. The other direction we just, in our lab, we doing the encapsulation of the PCMs. Basically, the idea is you put your PCM, the pure PCM, in the core, and you can apply a layers of polymer outside. It's like a capsule. So that means your PCM can be enclosed in a space. There's several advantages by using the encapsulation technology. First one, you can prevent the leakage of the PCMs, because the PCM, they transfer from liquid to solid or solid to liquid to give you the energy store and release performance. And if you without the enclosures, that means you have the leakage. You lose your function material. And secondly, because you enclose your PCM in a very small space, and it also improved the supercooling performance. So that's the main reason why we're doing this encapsulation technology. The third one is it gives you versatile applications by using the PCMs. So you can either use them in the powder, or you can compose them into fabric. Okay. So basically you have different, if you put them PCMs into different sizes of bubble, you have different encapsulation. So basically we focus on these tools, the nano PCM encapsulation and the micro encapsulation of PCMs. And the recent research we have done, because you put your PCM into the polymer enclosures, it gives you a better supercooling results, but the problem is using the polymer or the shell, and it has a very poor thermal conductivities. That means that your energy storage effectiveness has been reduced. So one of our other purposes for our recent research, we want to improve the thermal conductivities of the macro encapsulation of PCMs. So then we just compose some silicon nitride particles. They are in submicro size or nano size, and because it's inorganic particles, but your shell is organic, so you got to solve the interface problem between the particles and the polymer matrix. So we do some more surface modification, then we compose them into the PMMA, which is a polymethylene methacrylate polymer shells. And finally, after polymerization, we can have this micro encapsulation of the PCMs. And these are the research. Basically, we just add a different amount of silicon nitride. And we just proved that the particles has been successfully composed inside the shell. And this is the SEM microscopy of the micro encapsule PCMs. Like you can see, and this the size of the microencapsulation is about several micrometers, the diameter. And also we found after we composed the inorganic particles, the strength, mechanical strength of the microcapsules of PCM has been increased by 4 times. So this is another good outcomes of this technology. And we can find that the micro encapsulation PCM give you like a 66.4% of octane, which has a 121.11 joule per gram meter per gram for the latent heat. And also we have some evaluation about the thermal conductivity properties. Basically, the first we put our powders, micro encapsule PCM into the epoxy resin, and then we put a heater beneath that, and we can see we set up the temperature target. We see how long it will take to reach this temperature target of the sample. Basically, you can see the black one is the pure PCM, and the second one is a micro encapsulation of PCM without the inorganic additives. And you can see the thermal conductive has been reduced by encapsulation. But after adding the inorganic powders, the last line you can see, it can reach the target temperature about 25 seconds, so which is the quickest one. So that means after this added some additive, inorganic additive into the polymer shell, we can increase the thermal conductivities of this material. So currently in our lab, we can have like lab scale mass production. Basically, we can do like 1 to 2 kilo per day for the microcapsulation of the PCMs. Those are the equipment and our products. And also we do some applications of these PCMs. We compose them into the fibers, and we can see the fiber have like a smart temperature adjust properties. And also we put some in some like healthcare applications. So like the belt, you can have like good for your back. So. And also we have put some PCMs into the battery thermal management system. And on the right, the right picture, you can see after like 20 minutes at the same power level, after 20 minutes, the system with the PCM, the temperature increasing has been reduced. So that means it can be kept at a low level of the temperature. So this is some group photos from our group. And thank you very much for your attention. Why the salt? Because it's very cheap and easy to get it. Because in our institute, I mean, there's several candidates you can choose for these applications. Firstly, you need to look at the iron properties. So which iron is have a strong connection with the hydrogen bond, yeah, or weak, yeah. Yeah, the secondly is cost. So basically, based on these 2 points, we choose the sodium chloride. And because in Shenzhen, we are quite different from the main campus of Beijing. We focus on the last step to the industry. So every project we did, we want to transfer to them to productions. What do you mean you mean for the medicine applications? That's one direction we are carrying on now, because another direction in our group, we do some biodegradable fibers. So eventually we want to compose this into the fibers so it can be used in the medicine or medical instrument or applications. Yeah. Thank you. Okay, thank you.